A computer may be defined as a device or set of devices that can store data, and a program that operates on the data. A general-purpose computer can be programmed to solve any reasonable problem expressed in logical and arithmetical terms. The first fully operational general-purpose computer, electromechanical and using binary digits, was the Z3, built in Germany in 1941 by Konrad Zuse. Basically, there are two types of computer, analog and digital. By far the most common is the digital computer or microprocessor, which now plays a part in most aspects of everyday life. In this lesson, we will have a quick look at the analog computer, and then examine the numbering systems used to manipulate data in digital computers. An analog computer uses continuous physical variables such as voltage, pressure or mechanical movement to represent and manipulate the measurements it handles. Analog computers can have a very wide range of complexity. The manually operated navigation computer, with which you will become familiar, is a simple example of a mechanical analog computer. Analog computers are used as electronic models or analogues of mechanical or other systems in cases where conducting experiments on the system itself would be costly, time-consuming, or dangerous. For example, when designing an aircraft wing or any structure where motion can occur, the engineer must know beforehand how it will react to various physical variables, such as wind speed, turbulence, applied load, and temperature. In recent years, analog computers have become less popular because it is now possible to program digital computers to simulate moving physical systems. Normally, when working on paper, we count from 0 to 9, the decimal number system. Digital computers use a different system, known as the binary number system, to manipulate data. In the binary system, any number can be represented using only two symbols, 0 and 1. These symbols are used to represent the two voltage levels in a digital circuit. In the decimal numbering system, if a quantity larger than 9 is to be represented, then the symbols repeat by adding to the left of the first digit. Similarly, in the binary system, to represent a quantity greater than 1, the symbols systematically repeat by adding to the left of the first digit. In the decimal system, the least significant digit is on the right, and the most significant digit on the left. The same applies in the binary system. In the binary system, each digit represents an increasing power of 2. The rightmost digit in binary number represents 2 to the power 0, or 1 in the decimal system. The next, 2 to the power 1, or decimal 2. The next, 2 to the power 2, or 4. The next, 2 to the power 3, or 8, and so on. A binary number can be converted to its decimal equivalent by adding together the decimal value of each of its digits. We will use this table to convert a binary number of 101 to decimal. The 1 on the right represents 1 times 2 to the power 0, or 1 times 1, which is 1. The 0 in the middle represents 0 times 2 to the power 1, or 0 times 2, which is 0. The 1 on the left indicates there is 1 times 2 to the power 2, or 1 times 4, which is decimal value 4. By adding the decimal value 1 derived from the binary 1 on the left to the 4 derived from the binary 1 on the right, we get decimal number 5. Therefore, binary number 101 equals decimal number 5. You can see that by using the table, it is easy to convert binary numbers into their decimal equivalents. You simply place the binary number under the table. Note the powers of 2 above the binary 1s and add them together. For larger numbers, the table can be extrapolated as necessary. The table can also be used to convert decimal numbers to binary. To use it to convert decimal 423 to binary, move along the decimal value row from the left until you reach the first number equal to or lower than the one to be converted. In this case, it will be 256. Write the binary digit 1 under this column. We now subtract 256 from 423, leaving 167. This is greater than the next decimal value of 128, so we add a 1 under that column. Subtracting 128 from 167 leaves 39. This is less than 64, so we place a 0 under this column. It is, however, greater than 32, so a 1 goes under the 6th column. Subtracting 32 from 39 leaves 7. 7 is less than 16 and 8, so zeros go under the 5th and 4th columns. It is greater than 4, so the 3rd column gets a 1. 7 minus 4 is 3, which is greater than 2, so a 1 goes under the 2nd column. 3 minus 2 is 1, so the 1st column gets a 1. Therefore, the binary equivalent of decimal 423 is 1101000111. Where large quantities of binary numbers must be manipulated, a programming technique known as octal notation may be used. Octal notation is comprised of a series of groups of 3 binary digits, known as triads. Since the largest decimal number that can be represented by 3 binary digits is 7, this is a base 8 system. To convert a series of octal groups to decimal numbers, each triad is first converted from binary to decimal, then the decimal number is multiplied by a power of 8, depending on its position in the series. The resulting decimal numbers are then added together. The conversion can be done using the table shown here. The triads are placed in the table as shown. Each group is then converted to its decimal equivalent. Each resulting decimal number is then multiplied by its relevant power of 8. Finally, the decimal numbers are added together to produce the decimal equivalent. Octal notation is often used for the transmission of data by aircraft computers and their peripherals. Another numbering system in common use in computer programming is the hexadecimal or hex system, which uses a base of 16. It uses the numbers 0 to 9 along with the letters A to F to make up the 16 required symbols. This table shows the relationship between hexadecimal, decimal and binary numbers. The primary use of hexadecimal notation is as a programmer-friendly representation of binary coded values, which may otherwise be unmanageably large. As you can see, 4 binary digits can be represented by a single hexadecimal digit. This means that a 16-bit binary code, for instance, can be represented by a 4-digit hexadecimal number. Digital electronic computers use digital data in the form of binary numbers to perform their operations. This form of data is represented by only 2 levels of voltage as opposed to the analog system's continuous variables. The 2 levels correspond to on or off in an electrical circuit. All data is represented and can be manipulated using just these 2 levels of voltage. In digital computers, binary 1 is usually represented by a positive voltage of typically +5 or +28 volts, and binary 0 by 0 volts or earth. This is known as positive logic. In a number of less commonly used systems, binary 1 is represented by a negative voltage and binary 0 by 0 volts. This is called negative logic. term bit is used when referring to a binary digit. One bit is equal to one binary digit. If the system is using positive logic, a bit will either be a positive voltage to represent 1 or 0 volts to represent 0. A number of bits handled as a group are referred to as a byte. A byte typically contains 8 bits, but in some systems this number may be different. That is the end of the lesson. Here is a summary of the main points. An analog computer uses continuous physical variables such as voltage, pressure or mechanical movements to represent and manipulate the measurements it handles. Digital computers use the binary number system to manipulate data. In the binary system, any number can be represented using only two symbols, 0 and 1. A binary number can be converted to its decimal equivalent and vice versa using the table shown here. Octal notation is comprised of a series of groups of 3 binary digits, known as triads. Since the largest decimal number that can be represented by 3 binary digits is 7, this is a base 8 system. The hexadecimal or hex numbering system uses a base of 16. It uses the numbers 0 to 9 along with the letters A to F to make up the 16 required symbols. Digital electronic computers use digital data in their operations, and this form of data has only 2 levels of voltage. The 2 levels correspond to on or off in an electrical circuit. The term bit is used when referring to a binary digit. One bit is equal to one binary digit. A number of bits handled as a group are referred to as a byte.